Yeah, great to be here, everyone. A lot of great presentations up to this point. Learned a lot so far about vector databases and some interesting use cases, particularly around computer vision. And so we're going to do a little bit of a different presentation today. I don't think it's going to be as long as some of the others. It's going to be more practical. And so what we thought we would do is talk a little bit more about the machine learning development workflow when you're actually training or fine-tuning models. And a big part of that, in fact, the majority of the time that you've spent is quite often with data, as you know, this is a Voxel 51 meetup. Inspecting and interpreting the data is super important. And upstream of that, being able to search through and find interesting examples is also really important. And hence why we're focused on this topic of fast and flexible data mining for computer vision. Okay, so just before we dive into it, little intro about myself and Ayush. So LanceDB is a pretty new company. We were founded, I think about a year and a half ago. We're mostly located in the Bay Area. And I'm a founding product manager. I've been at LanceDB for about 8 or 9 months now, and Ayush has recently joined as well as a founding ML engineer, and he'll be presenting as well as me today. So just a little quick intro, the agenda. We're going to introduce the topic of data curation and mining with respect to computer vision, and talk a little bit about the challenges involved specific to computer vision. So, there are a bunch of different, obviously, modalities that we use with machine learning, but in particular, computer vision is something that has its own unique challenges. And because this is obviously a computer vision meetup, we wanted to focus on those. Then we'll talk a little bit about LanceDB, and I won't dive into, this is not a sales pitch, I'm not going to dive too much into LanceDB, but I think there's some interesting things that we're working on that can help to solve this data mining problem, particularly with respect to computer vision. And we also have an exciting announcement. I think it was shipped yesterday, I believe, into production, but we have now the LanceDB Voxel 51 integration, and we'll talk a little bit about that and where you can access the docs. And then I'll switch over to Ayush, who's also here going to present. And the rest of this talk is going to be sort of practical cases. And we're going to dive into a project that Ayush recently pushed out called YOLO Explorer, which is all about practical use cases to demonstrate how you can query computer vision data. And in the back end, obviously, that uses LanceDB. And then we'll finish up with Q&A. So to ground ourselves in this sort of machine learning development workflow that I talked about before, Karpathy has a tweet that I think he tweeted maybe about late last year. And he mentions this concept of the Tesla data engine. And he talks about the different stages that you go through in the sort of life cycle of this data engine, from data acquisition to then retraining, evaluating your models, deploying it, and then being able to track the performance of your models over time as well. And you sort of iterate through this loop over and over again. And what Karpathy advocates for and argues is that whoever can spin this wheel the fastest will actually be able to sort of create this data flywheel and improve their product at a faster speed than everyone else. And this basically forms the sort of principle by which the AI team at Tesla have been able to improve the performance of their self-driving car so rapidly over the last few years. But you'll notice that in this data loop, a key part of this is actually the data discovery and curation piece. That is being able to identify the anomalies or the inaccuracies that are occurring in production requires the ability to be able to sift through the data, be able to tag it appropriately, inspect and visualize it, with relevant tools like Voxel 51, and then send that to your labeling team to then go ahead and relabel or create the labels by which you can then improve the model performance over time. And so, but within this flywheel, there are a number of really key challenges. And we've been working with a number of companies to sort of walk through these challenges, and we've synthesized them into three big themes that we'd like to talk about today. The first one is scale. And so we all know that image data sets are pretty large, and that some interesting talks around video today as well. And video data sets are huge, right? And they're only getting bigger. And so being able to have the sufficient compute to be able to sort of generate your embeddings, store them, be able to search through these data sets at scale, the storage cost associated with them. Scalability is emerging as like a really big challenge for a lot of these companies when it comes to being able to search through data sets. Another one is around sort of like the ability to actually express what you want to in the query. And we've been talking a lot about clip today, which I think is a great example, because you can just take natural language, you can take text and go straight to the image. And so you can write, as expressively as you want to in a sentence, and be able to query across huge data sets to be able to find interesting examples. Obviously, if you sort of encoded that with captions that are semantically relevant to your query. But also what we've noticed is that rather than using unstructured search, there are a lot of our customers that also want more flexible ways of using search, like maybe it's using SQL as well to kind of create more something that's more deterministic, but also more structured, right? So if they have like metadata that's semantically meaning for their business, they can use a SQL statement and plug and play that as well. And also running clip embeddings on huge data sets might not be financially viable for a lot of companies as well. And the last area is data management. And this is more like, I'm sure for anyone that's been, developing machine learning models, versioning is super important. So it's not just versioning of the model itself, but also the data set. So you understand, okay, like what did I train on? What changed in the data set from the previous version? What did I add or remove to the data set? What version of labeling taxonomy did I use? There's a bunch of different metadata and lineage that's required in data management. And, a lot of the customers that we speak to have challenges in this area as well. So today, what we're going to do, we decided that we probably don't have enough time to focus on all three of these topics, but we're just going to focus on the middle one because we think it's probably like the easiest to demonstrate. And also like scale is a little bit challenging for us to we could show benchmarks and stuff like that, but I guess it's just not that interesting to show in a presentation. And we'll also touch on a little bit about the data management features as well. So to give some practical examples of like what sort of cases that you might want to search for, and this is in respect to self-driving, but you could extend this out to many different domains as well and use cases. It's not just limited to self-driving. But here in the top left corner, you've got hope you guys can see this. You've got a car sort of driving on a freeway, and then you've got what appears to be like a chair that's probably fallen out the back of that truck. And so, you've got this object like flying directly into view, I guess. And then the top right-hand corner, you've got a dog that's running beside a truck. Top left-hand corner, I'm sure a lot of you have seen these, trucks that I think they have like gas or petroleum in them, but they're reflective, and you can actually sort of see. It's almost like a mirror, right? You can see a car in the reflection itself. So like, you can think about, a classification model would just, detect that, hey, there's a car. But, who's to say that car is actually in front of you or behind you, right? Because obviously there's a reflection. And then the bottom, so the bottom right corner, you've got like cones, but the cones are lying flat on the ground. And they're not standing up. So again, all these like represent edge cases in our data sets that we want to be able to search for. And why is this relevant for sort of like vector databases as well? Well, more often than not, you want to be able to boost these data sets and actually sort of massage the distribution in a way that's going to boost the model performance. And sometimes these edge cases happen so infrequently, but you want to be able to find similar edge cases, right? So, whether or not that's finding similar edge cases from real world data sets, or being able to find examples and taking a few similar examples and generating synthetic examples, which a lot of machine learning teams are doing at the moment as well. This all involves basically being able to do some sort of vector search as well. Maybe combining that with traditional based keyword search as well. Again, just another sort of practical example here, and just to demonstrate the sort of complexity of how deep we need to go into these vision data sets to really understand, to get capture all of the distribution of what's going on. You can see here all the different types of stop signs, and within certain stop signs, you've got other stop signs that when you combine them together, they semantically mean different rules, right? So here you can see like except small cars. So there's a rule that applies to everyone except for a certain classification of car. And then just the sheer amount of like difference between stop signs that mean the same thing, right? Like the speed limit and the different design of like different speed limit signs as well. So this is why sort of data mining and data discovery is very, like, having flexible tools and being able to do this efficiently is super important for the problems that we face with computer vision. Okay, so to summarize, like what do we need to improve data quality then, right? Like we know that improving data quality is important. We know that the data has a lot of like interesting examples in it, and they're particularly challenging to be able to search for. What we would argue is that we need these three things at a minimum, right? And you probably need a bunch more of it. I'm just going to sort of highlight these key themes. Expressive and flexible way to query your data. Maybe you want to be able to query across the embedding space. Maybe you have some pre-computed features, either from your production system, your models, or maybe you do that on a sort of on a subset of the data, or you do that after you grab your data as well. So you're enriching your data maybe with more features. And maybe you have some metadata as well that you'd be able to query across. You want to be able to visualize this data easily. So you've seen these examples before. It's really difficult to understand what's happening in them if you can't easily like just pull them up and view them quickly. And this is why I think tools like Voxel 51 are super important. But not only visualizing them in the individual sense and at the object and patch level, but you also want to be able to sort of query and aggregate them, right? So look at the distribution, see how many examples do I have in a specific bucket, and be able to then refer to your model performance and see, okay, like, do I need to massage the data even more? How is this compared to my previous distribution, and so on and so forth. So when I say visualize, I mean both in aggregate and at the individual level as well. And the last thing, as we talked a little bit about, is like managing the data itself. Like when you append to the data or remove instances from the data, you want to be able to keep track of that over time easily. So I'm going to switch a little bit now to introducing LanceDB before we sort of go into the practical examples. And I just really want to focus on, like we've heard from a lot of great vector databases today, I just want to focus a little bit on the differences. So why is LanceDB a little bit more different than some of the other solutions out there? The first one is that we sort of really emphasize this notion of flexible querying. So we have a number of customers that just use vector search, or a number of customers that require full text search. Or before in the presentation, they were just talking about sort of the trade-offs, but being able to use semantic search and full text search, and maybe doing some re-ranking after that, building a pipeline. And so there's a lot of different ways by which folks want to be able to query their data. And so what we try and do at LanceDB is like integrate really well into how you want to be able to search, whether that's pure vector search, or whether that's keywords and SQL for full text search as well. You should be able to query the way that you'd like. We're also an embedded database, much like SQLite. in the sense that we don't have any servers that you need to run. So we actually run in process. So what that means is that, like let's say that you have, I don't know, like a Flask app running the backend, or you have like a Express Node.js app as well. You could, install LanceDB and run it alongside your application without actually having to like spin up another server. And your data can be sort of in place on S3 or object storage as well. I'll talk a little bit about that in a second. We scale pretty well. Won't talk too much about that, but we're heavily optimized to be able to scale on single node as well. And then we deal with multimodal data as a first-class citizen. And so with multimodal data, it's not just about sure, you can store the embeddings from that data, but it's also about actually storing the document data itself in LanceDB. So you can go ahead and store the images and point clouds and actually persist that in LanceDB to be able to manage that. Promise you this is my last slide on LanceDB before we continue. So one of the really unique things about LanceDB is that we're actually backed by an open source columnar-based data format. And so what that means is that we're optimized actually for persistent storage, and so a lot of the great other solutions out there for vector search, and rightly so, is optimized in memory. But we've taken a different approach. And so, we actually run on persistent storage. And to make sure that we've obviously optimized for machine learning workflows, we actually decided to create our own open source data format. And so what this means is that there's sort of zero lock-in as well, because it's open source. And so if you ever want to take your data and go to another database, it's compatible with Apache Arrow, so you can go ahead and export that and convert that to whatever data format you want, like whether it's Parquet or other, and go away and do your own thing. And so, yeah, we're basically heavily optimized for persistent storage and have much better performance than some of the other data formats out there. And we're growing pretty rapidly as well, which is great. Okay, and just another really quick announcement before we sort of get into more of the practical use cases, is that as of yesterday, I believe this is really exciting, Voxel 51 now supports LanceDB. And so if you want to check out how to use Voxel 51 Brain integration with LanceDB for some of the great use cases that I think were demonstrated before, like reverse image search and things like that, you can go ahead and look at go to the documentation that we've got links for there. Okay, so I am going to now hand over to Ayush, who's been working on this awesome project that we call YOLO Explorer. And the idea is to sort of introduce practical ways, I guess, to be able to explore, manipulate, and iterate on computer vision data sets using really simple APIs. And so we're going to walk through some examples and then talk a little bit about data management as well as we walk through these examples. So you shall stop sharing now.
All right. Hello, everyone. Thanks, Jay. First of all, yeah, I'd like to give a shout out to both Jimmy and Mark for handholding me through building this integration. And so, yeah, I hope you all try it out. It's super easy to use. No sign up, no whatever. It's just you can create as many indexes as you want and query your data. So I'll just give a bit of a context about this computer vision project. And I'm really excited to present something about computer vision, especially because this is Voxel 51. So I'll just share my screen and start. Okay, so this is called YOLO Explorer. If anyone knows me, I'm actually a bit biased because the context for this project is that over the last few years, I've been mostly working in computer vision, and I've had the pleasure to work with many tools, and I've worked on YOLO V5. I'm a core maintainer there, and earlier this year, I was one of the co-authors of YOLO V8. So we watch this field very closely, and we have had the opportunity to sort of interact with thousands of users. And as of now, we've almost answered around 10,000 issues related to real-time computer vision. And the general theme there is that there's a limit to the optimization that you can perform through the models. So most of those issues that you face in deployment or training or performance of computer vision models can be traced back to the data sets, right? So out of all those 10,000 issues that were solved, most of them could have been simply avoided by just looking at the data sets and performing simple optimizations, right? Here's the problem. Like, no one really wants to do that, because as the tasks get complex, the data set gets unstructured. Like, when you come from traditional machine learning in data science, you use CSV, which is pretty much all right. So yeah, so what I was talking about is that most of the issues that we face in optimizations can simply be solved when you trace it back to the data sets, try to make like simple adjustments, and you won't really need to sort of try around with changing model architectures, or even trying expensive model tuning or hyperparameter tuning runs, right? The difficulty there is that as the tasks become more complex, the data set becomes more complex. So it's really no way to sort of wrap your head around it, parse it properly so that you can actually view it. And so most users don't really want to do that, right? So which is why the tedious process of iterating over models sometimes to no avail. And so this is the project aimed to sort of showcase how, using LanceDB, you can sort of query your computer vision data sets, iterate fast, and then make quick judgments as to whether your data set is optimal or not, right? So let me start off. I guess let's just use this. Okay, so it's a short project, and so if you're on a Colab, you need to set this up like this. It's not available on PyPy. It's just a problem. But yeah, if you have set it up on your system, you can pretty much import it from YOLO Explorer. And again, it's built on top of YOLO, because obviously I'm biased, and I believe those are the best models. But so it supports all of the built-in data sets. And to get started with any one of the data set, you just pass in the data set, right? And it automatically download it. You don't really have to download anything. Of course, if you have a custom data set, then you would need to have it on your system. And just the one command that you need to run is called build embeddings. This essentially calculates the embeddings of your entire data set, and it does a lot more than that, right? It basically builds a columnar table that can be queried through LanceDB. And the good thing about LanceDB is that it has interface into Python data ecosystem, which means that there is no learning curve if you want to query, right? If you're a Pandas user, you can get the same table in Pandas. If you are a PyArrow user, you can get the same table in PyArrow, and you can also, there's also a native interface into SQL, right? So if you use that, you can also like query stuff like that. So let's look at the table that is formed and the schema, right? So you can just access the table using the table object, and then you can also access the schema. So let's see this Pascal VOC, which is probably one of the most common data sets for computer vision, how it's parsed, right? So you have the ID, which is essentially a row number for all practical purposes right now. The classes, the labels, of course, sorted so that you can actually make queries, boxes, and the image, which is stored in like bytes format, essentially to demonstrate that once you have the table, you don't really need the data set. So it can be used as an asset. You can like upload it as an artifact and things like that. So, and then vector obviously is the embedding. So yeah, once you have this, right, we can interface into any of the Python data ecosystem tools, which is the simplicity of this. You don't really have to learn an API to sort of start querying. Let's take a look at how you can query your object detection data set using, for example, SQL, right? So I can just have a query. This is a very simple query. Say select all from the table where the label is like person or cat, and I'm going to limit it to 4. So I guess I should open this up because, oops. Yeah, I can just sort of zoom in, right? So you can select, you can just query the data set using SQL, which is your typical object detection data set. There's nothing more than that going on here. Like, it's a simple data set, and we're just querying it using SQL. And when you like plot images and it accepts a query, it accepts even IDs. You can see the API in the GitHub repository that we'll share. And we get this sort of data, like top 4 results, right? You can do more than that. This is just plotting. You can also just interact using SQL to your data sets. So let's say I select all from the table where labels are like person and horse, right? So essentially means there's at least one person, there's at least one horse in the data set, and yeah, just 1 5 those. So it essentially returns Pandas data frame, right? So you don't really need to learn that API as well. We all know Pandas. So you run SQL, you get Pandas, and to plot them, I just need their IDs. So I'll just get the IDs, right? So let me just now come to a vector search, right? So the premise here is let's assume that you want to train a model which has a certain number of classes, person and horses included, right? And your model is especially struggling between person and horses. So definitely there is some problem with the data set. Maybe some images are obscured, and maybe there are some bad labels. So what we'll do is we'll just try to get some similar images. And this is where like vector search comes in, right? So you can just pass in any ID, any image, or even any blob file that essentially is an image, and it will just run through the database, and it will find you the similar images. I'm not sure if this is still in memory, but I'll try to run it and see. I guess not. Okay, the kernel is dead. Oh, no, it's there. Okay, so I can increase the count by any number, and it should still plot. The plotting should be a little messed up because it's a notebook, but yeah. So this is how like you can simply combine SQL, vector search, or any other interface for data management using LanceDB. And these are all Python tools, right? These are not new tools. So just to get some data set information, like what other classes are in this data set, this is just voxel. Sorry, this is VOC, not voxel. So VOC data set, and it has 15 classes, right? All right. More on like interacting between SQL and Pandas. So if you run a query, as I ran before, you will get a Pandas Pandas data frame, right? So here I see like I want to get all the instances where there are at least 3 people and a cow, right? So I get 6 images, and then I can double down on queries by using this data frame. So as you all know, like Pandas also can query stuff. So you can just double down on that. And now once I find the images that I'm interested in, then I can sort of plot them obviously, but then I can also like look for similar images, right? So I want to plot similar images to this particular ID. So this particular ID would definitely be the first image, and I can see what are the similar images to this, right? Now, coming soon to this project, probably like tomorrow, I just need to make an update, is pre-filtering, that you can also like pre-filter the searches, where you can say, you can build queries like, show me similar images to this, but take into account only the images from the data set that are like, that satisfy a particular condition. So that's coming soon. And then it's also really important. Vector similarity search becomes really important when you have to find out duplicates in your image. What happens when training specialized models is that they are pretty small, and the constraint of deployment is actually very, very tight, right? So you have to train a model really fast. It has to be really accurate, but it has to be deployed on edge device, right? So you cannot spend a lot of time in training, and you have to iterate really fast. So there have been some cases. If you look at some research, Coco dataset has a lot of bad examples, like a lot of mislabeling, a lot of duplicate images that don't add any real value to the dataset and stuff like that, right? It becomes really important. Like it's super simple to filter out that kind of bad images using similarity search and just writing your own script on top of it, right? So for example, this I just discovered when I was working on this project, that there are a few duplicate images. I mean, this is not really duplicate, because the cars are sort of, the distance between them is different, but this is like a curated image VOC. If you go to like higher, larger data set, higher dimensionality and stuff in terms of classes, especially Coco, you will find a lot of surprising examples of this. But yeah, of course, I'm running on a Mac, so I cannot just load up like 125,000 images. So yeah, you can just simply plot similar images. And I guess if it's still, oh yeah, I sort of messed up the plotting. But anyway, so this is the IDs, right? So yeah, pre-filtering is coming soon. Now I want to showcase one workflow that sort of is really important, is to iterate on your data sets. Like it's super simple to sort of find out the bad examples, maybe also find out the similar examples to the bad examples so that you actually pinpoint the issue. But the real problem is that you have to also iterate on your data sets, and you have to do it fast, right? So using the same tabular structure and Python dataset ecosystem integrations, we can also do that. So let's try it with a toy example, right? Let's create another Explorer object, and this time we're going to use Coco 128. But let's, for all practical purposes, assume that this is the Coco dataset with like hundred thousands of images, right? And the model that I will use for embedding is, by default, it uses YOLO V8N. Again, I'm biased. We can use any other model as well, but I prefer this because it's super fast. And I'm going to build embeddings again. And I'm going to set force equals true. Force equals true, essentially what it does is it basically rebuilds the embeddings even if it finds. So by default, even if it finds the embeddings and it searches, it sort of tries to match the dataset length with the embedding length. If everything matches, everything is good. It will just use that, but it will build embedding in this case, right? Now let's see an example of how you can enrich a data set using a second data set, right? So again, let's assume that there's an image in the VOC data set that the model gets confused on, right? So how we can sort of improve that? There are two ways, right? If you don't care about those examples, you can just eliminate them, but that necessarily is never the case, right? You generally have to sort of enrich, add more such examples and more such scenarios to sort of make your model see more of those stuff and get better at that, right? So what you're going to do is you're going to find, so we'll use the same person and cow image from the VOC dataset. Now, how to extract that image is pretty simple. Again, because we have like direct interface to Pandas and PyArrow, we can just get it, right? So without even knowing where it's stored and what's the location of the files and stuff like that. So I simply convert that to Pandas. I get the image blob and I get the ID. All right, now what I'll do is I just try to find the similar image to this particular image in another data set, which is the larger Coco data set, right? So I just find the similar images and similar IDs. Now I see, okay, these IDs are pretty much same as this particular ID that my particular image that my model was struggling on. So we have found that out. So let's just sort of plot them. So this is like, these are the images in VOC data in Coco data set, right? So let's assume that, okay, these are the images that we want. These are similar images to that scenario. Now, how would you add that to the original data set? All you have to do is you just have to say, call this function add images and pass the data set from which you want to add the images and pass the IDs that you've already gotten here, right? And that's pretty much it. Now you have a brand new data set. Of course, it's not persisted because it's a table. So you have a brand new image, brand new data set with these extra images and labels and everything that is needed to train them on a model. And it shows you the number of images after the addition. So we have added 10 more, so it becomes 10 more. And essentially, you have to persist the dataset. When you persist the dataset, it creates a link between them so that you have one dataset that combines all of the images. And you can simply start training with this command that it spits out, and that's it. Now you're training a new model with the new dataset. And you can repeat this step. You can write scripts to sort of do analysis on like 10, 20, 15 runs, and then you will find the optimal split, optimal subset, any of the other features that you want to that are interesting to you. And that is like how you can manipulate the computer vision data sets in real time, in real world, and without using any, without learning to use any other tool. It's simple: Pandas, PyArrow, SQL, or the tool of your choice. Well, I have like there are some advanced usages as well. Of course, you need to also remove images. What if there are some out of domain data set or data points in your data set? You can simply find them again using the same processes like querying, like finding similar images to bad examples, and you can just remove them and it will just be removed. You can just persist them again, right? So there's a simple workflow for sort of iterating over computer vision data sets, especially for YOLO models. And then it also sort of directly integrates to YOLO or Ultralytics package so that you can simply start training without any hassle. So it's like totally integrated. And there are some advanced usages as well. If you visit the repo, you will see that for advanced querying, there's something called similarity index. The similarity index, essentially, you can set the threshold of similarity. By default, it is 90%. But that percent is like essentially cosine distance. So that will change with the change in the dimension of the embeddings. So you should probably tune that to your data set. But I don't remember exactly which tuning this was like plotted on, but similarity index essentially gives you a count of how much similar a particular image in the data set is to the other images, right? And then you can tune that particular sort of top K or similarity threshold to get the kind of plots you want. And you can get this index using get similarity index. It results gives you a NumPy array where you can sort of run more advanced queries, right? Like you can run np.where to like get the data set or the kind of like indices that you want, and then you can remove them or add more of such data sets to merge 2, 3, 4 data sets of your choice and start training your models. So that's pretty much it. There are some other things that I'm working on this, but it's essentially like, a project to showcase the LanceDB integration with Python data ecosystem. So yeah, if you guys are interested, you can follow it along. It's at github.com/lancedb/YOLO Explorer. Yeah, if there are any questions, I have to answer that. And yeah, probably I'll hand over to Jay.
Awesome. Thanks, Ayush. I think we're over time. I'll just quickly take this question from Andre. So he says, talking about robo-driving, it's probably one of the edge computing cases of machine learning environment where no one has very little cloud resources. Are there anything specific narrowing in tech algo design choices? So yeah, this is a great question. There are a number of considerations that you'd want to take into account when you're building for production machine learning environments on edge. With self-driving, obviously, they probably have more compute than I would say a lot of other edge cases. Also an interesting thing about the compute that they're using is that it's usually very custom, right? So Tesla has their own custom setup and their own machine learning chip. And so, one consideration that you'd want to think about is, do you use a really large model or do you use a lot of small models for the production architecture? Because it could be that a larger model might have a better latency to performance trade-off, right, that you're looking at. Another consideration is you probably wouldn't be able to use all of the ops in either TensorFlow or PyTorch. Like there'd probably be some that are highly inefficient in terms of latency to run in production. And so when you're early on in development, you have to think about, what sort of operations can I actually use in my code that's going to end up in production, right? Because, and so it can be quite challenging because it's almost like this flexibility trade-off with the algorithm design. And another thing to consider is that usually what ends up happening is that the production code gets compiled into something that's running on custom hardware, and so that compiling process can be quite long-winded as well. And And so you probably want to be able to like work with the hardware teams to understand that a little bit more as well. So there's a lot of cross-team collaboration. So all of these considerations need to be taken into account when you're when you're writing machine learning software for edge devices. Hope that answered your question.